I worked on an audio game called Sonario with Gary Bishop. So it's an audio game of sound to understand sound. So when we first started this project, Gary said something that really struck with me. He said that everyone knows when visuals are wrong. No one knows when sound is wrong. We're not trained to know what sounds right. And this is something that I've definitely have come to learn. In my previous research in the Gamma group, I conducted a user study on how people perceive how sound reverberates in the room. The first couple subjects thought that small rooms sounded like large rooms. So we tried to, this was kind of our motivation for creating this. We wanted to figure out if there's a way we could teach people these concepts. So, how do you know when to cross the street? Well, you look for pedestrian signs, you look for stop cars. But what if you couldn't be able to see these? Then what would you do? Well, sometimes their crosswalks have little signals to let you know a sound, but not all crosswalks actually have that. Columbia and Franklin is one of those cases. Some of them don't have it. So you have to listen for cars. But I don't know if you've ever tried standing at an intersection with your eyes closed and listening to cars go by you. It's pretty hard to tell when they've all passed. Hopefully, yes, but it's definitely something you should try. It makes you realize what you're missing out on. So how can we teach these audio cues effectively? Well, in the previous user study that I did, we tried teaching them with videos, which was partly successful, but there are still a lot of people that confuse small rooms for large rooms. So we decided to pick something that's more interactive to make a game. So the idea for this game is the player's in a cave, and the only interaction is the sound they create. So that means it's just like a cane tap on the ground. It's just like walking with their footsteps, or when they run into a wall, it should make a sound. That's all the interaction is. That's all the game mechanic is. And the goal is they have to find their way out. So hopefully they'll be able to understand how the sound reverberates and hits the wall to let them know that there's an obstacle there. And when the sound doesn't go through the doorway, then you know that as you're in front of an opening and the sound doesn't reverberate back to you as quickly, then you realize, oh, this is an opening. I can go forward. And so this is something that we want to try to do. So you've probably seen caves in video games. This is Skyrim. It's pretty well lit for a cave, to be honest. This is Dear Esther. You can see the stalactites coming from the ceiling, and it's all reflecting light. Well, this is going to be my game. It's going to be completely black. There are no visuals. So everything's going to have to be communicated by audio, letting you know how to interpret the environment, what they should be doing and where to go. We want it to be able so that anyone can play. So we decided to make it browser-based. Most people have computers now or have access to computers. And so this is some way that everyone can be able to learn. And the last constraint is it's got to have 3D audio. So the different aspects of 3D audio is spatial sound, reverberation, diffusion, and diffraction, to name a few. So spatial sound is obviously the most important. It helps you localize the direction of where sound's coming from. And reverberation is the second most important because it lets you know what's going on in your environment and how the sound is interacting with it. Then diffraction. So that's just letting you know if there's someone outside of the room and you're in the room, then the sound of the person talking can still reach you, even though you can't see them. And then diffusion is when sound, because of the texture of the walls, scatters more than if it was a smooth surface. So we need these all to be cheap, and we need it to be fast. So spatial sound, to explain it more, it's different sound comes to your ears, and it comes at different times. And your brain is trying to interpret it to determine which direction the sound is coming from. So we use head-related transfer functions to simulate this difference in sound. It's typically different for everyone, but you can definitely you can generalize it so that it works for the average person. And then for reverberation, so I'll do this example. You have this orange cat on the left, and a white cat on the right. So the orange cat's trying to talk to the white cat. So this is the direct sound, the direct sound that the cat's saying to the other cat. And then you have first order reflections, and this is like a one wall bounce. And you have second order reflections, and it means it's bouncing off of two walls. And higher order reflections is then greater than two wall bounces. So the early reflections, they enhance your perception of the sound. So, you have your direct sound, and then the sound should be reflecting quickly off of the walls. So understand how your environment is. But then late reflections, so the higher order reflections, obfuscate your sound. So like as you keep talking and the room keeps reverberating, like from your original sound, all your words start getting garbled together, which isn't always clear to understand. So something more specific about reflection, you have specular, which is, it's a smooth surface. So you're able to predict for all rays of sound that are hitting the wall, you can predict the angle that it's going to go out of. With diffuse, it's a rough surface, so depending on where it hits, it could be reflecting in a totally different direction. So it definitely like messes up how you expect the sound to be reflecting. And then we have diffraction. So you can hear the sound without seeing their source. So you have the cat, the orange cat can't see the white cat because there's a wall in the way, but the sound from the cat is bending around the wall to reach the listener. And this is something that we want to try to simulate. So how does sound simulation work in games right now? So if you haven't guessed by now, sound propagation is really expensive. You have to calculate for every object, for every wall, every sound source. So for most games, they use a reverb filter for reverberation. What this entails is, they compute what the reverb delay is for the room. They can either use expensive equipment to figure out, measure the room and all like how sound reflects off of it, or they can just guess and be like, yeah, that sounds right. So how it works is so say this is my reverb zone. You come into it, you make a sound, and it will reverberate in that reverb zone. But when you leave, it'll stop reverberating. But when you're in the zone, the reverberation is typically always the same because of that reverb delay that you chose. So when you get closer to the wall, it doesn't always you don't get that feedback of the sound instantly hitting against you. So it's not dynamic enough. So how is sound simulation in my game going to work? Well, it needs something cheap, but it's got to be more accurate than a reverb filter. So we decided to focus specifically on first order reflections because we figured this would give you the most feedback of your environment. So how do we do these first order reflections? Well, we're using the image source method, and how it works is instead of calculating the distance from the source to the wall to the listener, what you do is you take the source, you mirror it across the wall, and create the mirror image. And then the distance from the mirror image to the listener, it should be the same distance as if you had calculated the whole bounce. So it's definitely a lot cheaper than all those computations. So how does this work with openings? How does it work with doors? So to create the mirror image, the reflected sound has to be perpendicular to the wall. If it's not, as you can see here, it causes an n greater than 1 reflection, which we decided not to do. So in this game, the listener is the source, so it requires you to move through the environment to understand that there is an opening right in front of you. So as you get away from the wall in front of the opening, you should hear that there is no bounces going off on either side. So in addition to this, we also use a sound cone. So this approximates the volume and the direction to help you localize where sound is. So you have the source and you have the listener. So the source to the listener is going to be, the initial volume of the source. But if you're outside of this inside cone, it'll have kind of a drop off on how loud the sound is. And so the further away you get from the initial inner cone, the less you'll be able to hear. So it's if you're looking a different direction, you shouldn't be able to hear me as well. So the question is, this is all great theoretically, but how does it actually work, and how does it actually work? So we compared reverb with no reverb in a small and large room, and we took samples from the middle and then the left side of the room. So on the left, we have no reflections. All you see is like the direct sound, the positions in the middle. And on the right, you have direct sound, and there's an echo from the small room that you're in. So I have sound examples. We'll see if you guys can tell the difference. Usually it's better with headphones. That was the first one, which is the direct sound. And then here's the one with the echo. You can tell the difference, right? So then we tried it again, but we moved the position of the listener. So the first sound will be the direct sound. And then the second will be with the echo. You can't quite tell with this speaker system. But I don't know if you could tell, but on the right, the echo moved closer to the initial sound, which is what we expect because you're closer to the wall. So this is actually exactly what you want. And then we also have another echo, which should be from the other side of the room, which is also what we want. So we tried this again for a larger room. I'll play the sounds. We'll see if they sound louder. I don't know if you heard the echo there, but so the first one, you're right next to the wall, and if you can tell, there's the echo from the wall that you're right next to, and then there's an echo from the front and back wall, and then there's that little dot over there is an echo from the very opposite side, which in a large room is exactly what we want it to do. It should be smaller in amplitude than the rest. And then the image on the right, the echoes are all kind of at the same time, which is because you're in the middle of the room. That's actually what we want. So in conclusion, sounds hard to get right cheaply, but interaction is definitely the better way to go in teaching them all these techniques. So for the future, we hope to increase the orders of reflection to see if you can tell a difference between if it enhances your perception with more than one order of reflection, and to add a more accurate diffraction and increase the difficulty of levels by combining all of these together. So you should come check it out on Maze Day on April 28th. Shameless plug for Gary Bishop. All right, that's it.
Questions?
Yes?
So how do you handle with how you're simulating reverberation? Since obviously audio propagation is a single sort of direct line, you have the audio fanning out as it's going along. How do you deal with that with intersections nearby openings, for example, in the door case that you were showing?
So yes, it does fan out, but this is why we're using the sound cone, for example. So if based off of the direction that you're facing, that's the sound that you're creating, the sound that you're listening for. So I mean, even though it does fan out, you shouldn't be able, you won't be able to hear all of that. So yeah.
So you get a higher order reflection thing. Can you use something equivalent to ray tracing for rendering? Could you do that for sound?
Yeah, that's what they typically do, but it's still very computationally expensive. Yeah.
So what do current systems implement typically? For example, like OpenAL?
I'm not sure what OpenAL uses. So I can't really answer that question.
Okay. Any game that you're aware of, what types of?
So most of them don't simulate. Most of them use fake techniques like reverb filters. That's why there's a lot of research in sound simulation right now, and in the Gamma group, where they're creating their own sound engine to be able to create all of these accurately. Yes.
So do I assume that your game is actually combines some sort of turn thing, make sound, turn, make sound, turn, make sound?
So how it works is there's no track. You can create the sound whenever you want. And so as you move around in the environment, you can hear the instant feedback of the sound that you're creating.
But you're moving in the virtual.
Yes. Yes.
Every time you step, you get a sound, or
Every time you sit up, you hear your footsteps but then you can also create a sound that's more reverberant.